So now this is the video of the dust flame. Here the concentration, so you can see that as the premixed methane and air comes out of the nozzle, based upon its momentum, some amount of dust will entrain. We can monitor how much has entrained by knowing how much has come into the burner from the holder, which is kept outside the world. We know what is the initial mass and final mass, from which, if you know the how much mass has come out and the volumetric flow rate of the mixture, I can get what is called the dust concentration in gram per meter cube. So for 50 gram per meter cube, for an equivalence ratio of say 0.8, we can see that this is the image. So we can see that the inner flame is not at all visible, because actually speaking here the hot air is supplied. Basically you can see hot air is supplied, so the dust actually burns nicely over the hot air, and after a particular distance it just goes away. You can see the radiation properties here, luminous zone, etc. is shown here. So this is the characteristic of a dust flame. A streak of hot particles come out, and you can see that it is actually it's laminar only because of the fact that the flow rate is very small. So this is the characteristic of the dust flame. So you can observe that the dust takes some amount of time to release its volatile, and gas phase combustion occurs. Once the gas phase combustion occurs, that heat, that flame, premixed flame which is formed, that will try to heat up the char, and the char also receives oxygen from the ambient and it burns. So you can see that the volatile combustion is expected to finish in the luminous zone, and the char combustion extends to some height where you can see that the char is converted. After that, based on the particle size, unburned char may go out if it is bigger particle size, or if it is very small, the char will completely be converted and only ash goes out. So now let us see some features. The laminar burning velocity. So SL, you have put SU here. This velocity in meter per second for several equivalence ratios, several particle sizes, several dust concentrations is given here. So for example, when the coal dust concentration is 0, so this indicate the base case, there is no dust. So there are 3 equivalence ratios. The rhombus is 0.8, triangle is 0.75, and the square is 0.85. You can see that there is a value of 0.75, 0.85 and 0.8. Some values are there for the SU, that is the laminar burning velocity. This is methane and air. Now when you add dust particles, a particle, first what happens is, so there is a flame, a premixed flame, the particles passes through the flame. As it passes through the flame, the particle is heated up. That means TF decreases, the flame temperature will decrease because the heat is taken up by the particles. Several particles will go through the flame, correct? So based upon the concentration and the particle size, so you can see that the lowest particle size is about 25 microns range, highest particle about 90 micron range. So you will see that as the particle goes into this, based upon the particle size, it will take some time to get heated up. So all the small particles, because of the higher surface to volume ratio, will heat up much faster. When they heat up much faster, they release the volatiles also much faster within the flame zone. So for small particles, the volatile release may occur within the flame zone, around the flame zone itself, like this. But larger particles may heat up and go and release the volatiles away from the flame. It is possible. So the rate at which it is going to be heated up will cause basically the release of volatiles. Okay, now this flame has some phi value based upon the mass of air divided by mass flow rate of CH4. But once the volatiles are released, here volatiles are released, this phi will change. Basically, phi will increase or decrease. Basically, what happens here? The phi will only increase because only fuel is added. Fuel is added and the phi will increase. Okay, now that is one point. Second one is phi changes. So now we are looking into lean fuel equivalence ratios. So now when phi actually, I will say phi increases. As phi increases, SL will increase, or I can say Q dot will increase. So that means TF also will increase. Correct. But you can see there are contributing things. Particle getting heated up, flame temperature decrease. But phi increases because of volatile release. Volatile released, so phi increases, so Q and TF increases in the lean, from the lean to the rich, I am saying. So now we can see that there are contradicting effects. Based upon the combined effects of these two, either I will have a increase in SL or decrease in SL. So we can see that for most of the cases, especially when the particle size are 75 to 90 micron or 53 to 60, all these cases you will see a decreasing trend in the SL when the dust concentration is increased. Only one case, this triangle, you can see there is an increasing trend. When the particle size is very low, equivalence ratio also is very low, then the volatile release increases the equivalence ratio, the particle heat up is much faster, the flame temperature does not decrease much because of the small particle size, etc. This contributes to increasing SL. In other case, this heat sink effect of particle getting heated up causing decrease in the flame temperature causes decrease in the SL also. Okay, so these are the interactions between the particle and the premixed flame. Do you understand? So there are two effects: particle sensibility, particle draws heat from the flame, flame temperature decreases. Then volatiles are added to the gas phase, changes the equivalence ratio. Equivalence ratio is bit increased, so Q dot will be increased and TF also will be increased. But combination of these two can be such that where the volatiles is released, as I told you, for small particles, volatiles are released within the flame zone itself, contributing to increase in the flame speed. But in the case of bigger particles, the volatiles are released away from the flame zone, not contributing to the flame speed, increase in the flame speed. Now we move on to the other topic, which is dust explosion. So we have seen dust ignition, spontaneous ignition of a dust layer in a hot chamber or hot plate. Second, we have seen the deflagration of dust, where the dust flames, etc. are discussed. Then the third will be dust explosion. Here we will have, so let us first consider a gas air mixture, fuel gas or explosive gas, hydrogen, okay, like hydrogen, C2H2, etc. very reactive gases with air mixture. Then we can also consider flammable vapors, mists, then dust clouds, etc. What happens is, how much they are reactive, that is indicated by if they are confined in a vessel of certain volume and ignited, reaction will take place. This reaction causes pressure increase within the chamber, and the rate of pressure rise is called deflagration index, capital KST, deflagration index. This is one of the characteristics. Second one is the maximum pressure reached for a given configuration. That is, what is the volume, what is the initial temperature of the mixture which is present, or cloud temperature, or what is the equivalent ratio, etc. That will contribute to P max. Okay, now this reactivity, which is a combination of these two factors, deflagration index and the maximum pressure, are determined by conducting experiments in constant volume explosion vessels starting from a capacity of 20 liters to as high as 1000 liters. So, it is very simple experiment. So, let us take a spherical vessel, mixture is injected, this explosive gas air mixture or whatever mixture is injected into it, and I get the ignition done. Then it is homogeneously mixed, so that please understand that there will be some time for increasing, but based upon the reactivity, how much fast the pressure, that is how rapid the pressure rises, that will indicate the reactivity. The pressure can vary with temperature or time, like this and get down after vent is open, or it may happen like this. So, how fast the pressure rises to the maximum value, that will indicate the reactivity. Okay. So, there are tests, standard tests to determine this, and these parameters like deflagration index and maximum pressure is important, where you really consider applications having enclosed vessels in which combustible mixtures are handled. So, concept of using an explosion sphere for flammability studies, that is, when there is ignition in the center, a spherical flame is formed around the ignition location, and it slowly propagates. The radius of the flame increases, pressure also increases. So, that is the concept used for example, if the radius has become a kind of to a finite value, that is flame radius has propagated to a finite value, then we can say the mixture is flammable. So, explosion sphere was also used for conducting the flammability studies of premixed flames. Several authors have done this. Now, in this same thing, if you can measure the pressure time variation, then we can calculate the spherical flame propagation, also the explosion indexes. So, now this is the 20-liter explosion sphere, ASTM E1515 2010 is the standard. That is one of the thing. Then second one is 1 meter cube explosion sphere, 1 meter cube explosion sphere. So, here this is shown, and here you can see Professor Rangwala from WPI, who is the author of the Mechanism of Fires. So, huge, very huge explosion sphere here. So, this type of apparatus are used to find the dust explosion basically. So, you can see the components in this. To measure the pressure, a high speed pressure transducer is kept. It is a very rigid vessel, very rigid vessel. Then there is a dispersion nozzle, then dust reservoir. So, you can see the dust reservoir and dispersion air. So, this air will be injected at a very high pressure, so that the dust will be dispersed into this reservoir, from this reservoir into the chamber. Okay, there will be some quartz glasses, you can view what is happening inside also, and simultaneously measure the pressure. Okay, now the ignition is caused by electrochemical igniters. There are igniters. So, once you disperse a certain volume of air impulsively, that will carry the dust and form a cloud in this particular vessel or a sphere, whatever you say. Then the igniters are simultaneously turned on to cause ignition. Once ignition is occurred here, you can see that the ignition occurs at the center. Then we can see what is happening to the window, how the flame propagates, etc. Simultaneously I can measure the pressure as a function of time because it's a high speed pressure transducer. Okay, so this scale 20 liters, 1 meter cube, etc., are required to categorize the reactivity of several flames, dust flames. So, standard dust explosion vessel is equipped with vacuum. First, you have to take it out. So, vacuum, then dust dispersion, ignition, and pressure sensor systems, as we explained here. So, the dust cloud should be homogeneously created. Okay, the dust and air cloud should be uniformly dispersed into the volume. Then simultaneously ignition should be caused. Okay, so what we get out of this is the pressure trace from which we can quantify things. Okay, a measured quantity of a dust sample is placed in the reservoir, dust reservoir. So we know what is the mass of the dust. So go back here in this reservoir, I keep known mass. So here this dust will be characterized by particle size and its distribution. And of course the mass. Now air, as I told you, from the dispersion air nozzle, it is injected at high pressure so that this mass is injected into this, as well as when it is injected it will also form a dust air mixture, almost uniformly distributed. But as we have discussed before, this mixing will not be as microscopic or molecular level mixing as we see in a fuel gas mixture. So this dust air mixture will be as uniformly as it is mixed, but it is not going to be thoroughly uniform. Okay, anyway, that is not a problem. This thorough mixing can occur only depending on the particle size. That's all. That's what several factors affect the mixing or the entrainment and mixing. What we have already seen, lift and mixing. So the dust mixture, as the air is injected through the dust reservoir, will be discharged into the vessel. So fast acting valve and rebound nozzle is used to do this. Okay, nozzle means you have to have a high pressure air coming out of the nozzle, creating a high velocity, throwing this dust also with this, and this momentum will also cause the mixing. Now this dispersed dust cloud is ignited after a specified ignition delay time, very small time. Why this time is required? Because the dust has to go and settle. This cloud has to settle in the entire volume. For that, some time is given. Okay, after this ignition delay, ignition source at the center, typically using two chemical igniters of capacity 5 kilojoules each, is positioned in the center of the vessel and it is going to cause the ignition. Now we can have the high speed pressure transducer to measure the pressure versus time. This is pressure versus time, and we can also get dP by dt versus time. So you can see that the pressure during injection increases slowly as the dust air is injected. Then you can see that it is settling down here. The pressure increases as the injection is continued. Once the injection is done, here there is some time which is given. That is the ignition time delay, after which ignition occurs. Once after ignition, you can see the very high rapid pressure increase within a short duration of time from the low value to the high value. So this is delta P. This is maximum pressure. So that occurs, and after that the combustion is etc. complete, then there will be decrease in pressure. Then we can also release the pressure by opening some valves etc. so that the pressure decreases. So you can see that this pressure time history will give you the maximum pressure, which is an important characteristic. How fast from the ignition point, so this time, how much it takes, or the dP by dt max, that will give you the rate at which pressure increases with time, that will give you the reactivity of the dust. So this is very important. Okay. So now after getting the pressure max, we can calculate the KST, deflagration index. Explosion mitigating measures like providing explosion vents or suppression system rely on empirical correlations which involve deflagration indices like kg in the case of gases or KST in the case of dust flames, plus what is the maximum pressure which is attained for a, see, basically that will be, this is also a function of equivalent ratio, unburnt temperature of the mixture, initial mixture, and so on. Okay, now kg or KST, okay, is determined by the maximum rate of pressure rise. That is, once I get the pressure time history, I can get the dP by dt versus time history also. So Deho et al. In 1996 has given an expression considering a spherical vessel or explosion vessel of volume V naught. To determine KST, he has used this expression dP by dt as a function of time, maximum, wherever it is maximum value of this, into V naught power minus V naught power 1 by 3. So KST is dP by dt maximum. So go back to this here, this value dP by dt maximum, this value into volume power 1 by 3, that is given as deflagration index. So obviously deflagration index involves volume of the explosion sphere itself. That means the size of the explosion sphere will affect the value of deflagration index. So then what it means? That means the investigation of dust flame is rather difficult because it is going to be, see, for example, if volume is increased, then probably you can, there are situations like this. See, dP by dt maximum may not be very high because of the concentration of dust cloud there, or the equivalent ratio etc. will be low. The pressure rise may not be very high, but volume can be higher. In this case, the KST value can be low. In other situation, the dP by dt can be higher, volume can be low. In that case also, KST will not be very high. In some cases, there will be huge volume as well as huge like concentration of dust, and reactivity of the dust is also high. In that case, KST will be large. So we can see that several situations can occur. So it is slightly complicated to do the hazard classification. That is a problem here. Okay. So why this happens? Because of the onset of turbulence. So in the spherical vessel, when the center is ignited, for example, the flame forms and propagates, but this is not going to be a spherical formation, a spherical propagation of the flame itself. It is very rapid, although, so it is not going to be very laminar in nature. So what basically happens is there can be turbulence which can set up, and some cell formations etc. can occur. So this onset of turbulence will cause more complexity in this as the volume increases. Okay, but in practical situations we are not going to restrict the volume, correct? So this is the complication. The KST value depends upon V naught. As V naught increases, onset of turbulence comes into play, and that gives more complexity for classifying the hazardness of the dust explosion. Okay. So the effect of turbulence, here you can see that increase in the turbulent intensity with the expanding combustion products. That is the reason basically which causes the the assertness. For example, what happens when there is a, as I told you, there is ignition, a small laminar flame forms. Okay, then there is some oscillations in the flame, you can see here. Now this has become on, this is full laminar flame, you can see a clear circular spherical flame. There is edge oscillations, so turbulence is now onset slowly. Then after that you can see in this time it is fully turbulent. So in each of the case the turbulent intensity is very low here, then turbulent intensity increases, but explosively or exponentially it increases as the time propagates based upon the vessel. So this turbulence etc. will cause oscillations in the measurements. Okay, so that is the important thing. So this figure which Rockwell and Rangwala has shown, schematic of an expanding flame thread for different times T1, T2, T3 and T4, where the turbulent intensity is increasing with the flame acceleration. The flame actually accelerates because of the increasing surface area, correct? The flame, these are all unburnt mixture. The flame surface area is spherical here, it is also spherical here but with some oscillations. That means the area here will be slightly more than the area of the sphere, but if you take this, the area here will be much more than the area of the circle or the sphere. So that is the problem. So the turbulent intensity increases, causing the flame to accelerate. That is the effect of turbulence. So now people have also categorized the particle turbulent interaction. Basically, first one is, so in the gas phase it is very simple, but if the particle is there, go back here, these are if this is only a homogeneous mixture, no issue. Yeah, the situation is somewhat different. But if there are particles, the particles are interacting with the turbulent eddies or the turbulent flame itself, how the interaction will be, that is what is discussed here, the particle turbulent interaction. First of all, there are three types: inert, pyrolyzing and chemically reacting particle. Okay, let us say inert particle, like say ash or sand particle, they are not going to react, they are going to only sensibly get heated. Then you say there is a coal particle or biomass particle etc. Then it will pyrolyze, volatile gas will be released upon heating. And third is the particle itself can burn. The same particles, coal, biomass particle can also burn, chemically reacting situation. So now what happens in the first case, the composition, because it is ash or sand, okay, maybe silica, some minerals etc., the composition and shape of the particle are not changed. Only the turbulent mixing process will be affected. Now when pyrolysis gases come out of the particles, the type 2, then a gas layer of pyrolysis particles exists between the particle and the gas phase. Okay, this is pyrolysis particle, pyrolysis gases are coming out, and there will be a layer of gas. This is the flame, and there will be a layer of gases between the particle and the flame. So this can affect the local turbulence also, and the local turbulence in turn can affect the pyrolysis rate. So that is the complication in the pyrolysis. When there is type 3 where reacting particles are present, then what happens is the interaction is more complicated because heat release also happens. Heat release also happens in the combusting products. There can be local flame there. This flame can also interact with this. So pyrolysis plus reaction, these rates can affect turbulence, and turbulence can in turn affect these rates.